All right, let's get started. I'm Ruxian Wang, a professor from Johns Hopkins Caribbean School. Today, I'm going to give a tutorial presentation on discrete choice models and applications in operation management. I think nowadays it's fair to say we make choices every day. Think about a scenario. You want to purchase a computer. There are many options. Which one are you going to choose? Which one are you going to buy? Different computers have different features at different prices. Discrete choice models can help us to describe consumer choice behavior. Discrete choice models are concerned with how individuals make choices among multiple items, like the products. Important topic, it's very important topic in economics, marketing, transportation, and operations. How to formulate choice model, how to formulate the choice behavior. Some researchers start with the choice axioms. They derive choice models, like the famous loose model. Others consider utility-based choice models. For example, the Hotelians model or the random utility maximization-based choice models. Or we can use some existing models to approximate consumer choice behavior, like the Markov chain choice model. We often consider rationality or bounded rationality in consumer choice process. Choice models are interdisciplinary concepts. In economics, researchers consider discrete choice models with a random utility. Sometimes they also incorporate search cost into the search models to develop a hybrid model that consider search behavior and also choice behavior. In marketing and operations, researchers consider product variety management, including substitution or complementarity effects. Rationality is often an important topic in consumer, the purchase process or consideration set formation process. In statistics or applied mathematics, researchers try to develop efficient algorithms to estimate the choice models or to calibrate the parameters in the choice models for different data, different structure. For some operations problems, it may be hard to find the optimal solution, so we can consider some approximations, like the fully polynomial time approximation scheme, the FPTAS. In operations management, we consider operations decisions like price optimization and price competition. Now we can also consider assortment planning, the firm to decide how to offer a different product set to different customers in different scenarios. Let's start with the loose model. Loose model may be the most commonly used discrete choice model. Loose is the mathematical psychologist. He proposed the loose model. He started with the choice axioms. The idea is very, very simple. Basically, it says the choice probability for any item I in the set S is equal to the choice probability for any subset S prime in S times the choice probability for any product I in the subset S prime. This is true for any subset S prime. We call it path independence property. If this is true, we can say there exists a unique positive real value attractiveness AI for any item I, and the choice probability for any item I is equal to AI divided by the sum of Aj for any j in the set S. It's a very, very elegant formula. We call it loose model. Loose model is easy to verify, for example, by the IIA property. It says the independence of irrelevant alternatives. The ratio of choice probability for any two items, I and j, is independent of the third item, k. If this is true, the choice model must be the loose model. In the random utility maximization framework, rational individuals make choices among multiple items. We often use the term representative consumer. The utility for any item I is equal to this part, this formula. Basically, it says the utility can be divided into two terms, I, little I, and Kasa I. Little ui represents the nominal utility accounting for the valuation of product attributes. And this term is deterministic. The second term, Kasa I, is a residual utility, is ex ante random, indicates consumer-specific idiosyncrasies. The realization can be different for different consumers. Sometimes we call it first degree of customer heterogeneity. The representative consumer chooses item I if its utility ui is greater than the utility for any other item j. The random utility maximization of the round model has been well studied in the literature. Today, we are going to talk a lot about the random utility maximization framework. On this framework, we can develop different choice models. The multinomial logical choice model, I think we are quite familiar with this model. Because of the nature of this tutorial presentation, I want to spend some time on this very basic, very famous choice model. Let's say the available product set S, and the utility for any item I in S, as we said before, has two parts, little ui, the deterministic utility or the nominal utility, and the Kasa I, a random utility term. Sometimes we call it the noisy term. Actually, the deterministic term, the nominal utility, can be read at the attribute level. Here, xi is a vector, represents the attributes for product I, and v is another vector, is the attribute coefficient. And random utility maximization framework says the consumer chooses the product with the largest utility. So the choice probability for product I in S is equal to the probability ui is greater than any uj, as we said before. Actually, here we can have the closed form expression for some special case. We further assume the random term Kasa IID random variable with a Gamble distribution. Here's the CDF for Gamble distribution. Here we have parameters, the scale parameter mu. And you can see there's the CDF. Sometimes we call it a double exponential distribution or type 1 extreme value distribution. And we can get the PDF. For this one, we can have the choice probability in closed form. Again, the choice probability for product I. Here I briefly show you how we can derive the choice probability in closed form under the IID Gumbel distribution. Here, this is very basic. I won't get into detail. Probably you may want to do some research on discrete choice model. You may want to incorporate some new features into some existing choice model, like the MNL choice model. Here, I want to show you how to derive the MNL model in closed form, and you may be able to derive a new choice model also in closed form or near closed form. That is very important. All right, here you can see we use a double exponential distribution. And this part is very, very important. We introduced two new variables. The first one, AJ, we call it attractiveness for any item J in S. And the other one is ZI. ZI is the exponential of minus I divided by mu plus gamma. Gamma is constant. Actually, it's the Euler constant. Euler variable that's equal to roughly 0.5772. Then we can have the MNL model in closed form. You can see it's a very, very elegant model. We have numerator, we have denominator. Here you find this one is exactly the same as the one we just said before, the loose model. Economists prefer to call it a loose model because the model was first proposed by Loose. Researchers from other areas prefer to call it the MNL model because it's probably more intuitive, right? We have the MNL model, and when we talk about application, when we talk about data, how can we use the data to estimate this discrete choice model, how to calibrate the model parameters. Let's briefly talk about the basic stuff, the data structure. The data is the aggregated data. It can be individual choice data. And we have k choice scenarios or k sailing period. In each choice scenario k, we know the product offset, and we know the product attribute value. When we talk about computers, we know CPU, we know RAM, we know screen, and price can be one of the attributes, right? We know the attribute values, but we don't know the coefficients for the attributes. How, what's the relationship between the product nominal value and the attributes. Here we have a set of unknown parameters. We call it an attribute coefficient V. On a linear attribute utility assumption, we can write down the nominal utility. Here, this part is the nominal utility. And we can write down the choice probability and QKI. Even the data is complete. We know the outcomes in each scenario for any product, right? In particular, we know NKI consumers who purchase product I in each scenario K. We also know the outcomes for the no purchase option. Here, NK0 customers chooses the outside option. And we can write down the likelihood function and also the log likelihood function for general choice models. Actually, for the MNO, the log likelihood function becomes much simpler. You can see here is the log likelihood function. We can take the MLE, maximum log likelihood function, estimation approach to maximize the likelihood function or the log likelihood function. And actually, McFadden shows the log likelihood function. This one is jointly concave in V, so it's very easy to estimate. A little bit more detail about the concavity of the log likelihood function. Here is the log likelihood function for each scenario K, and we consider the derivatives. This part is quite important. And for the Hessian matrix, and we can find this one is the negative semi-definite, because the Hessian matrix can be expressed in this way. You can see inside the square bracket is a positive semi-definite. So the Hessian matrix is negative semi-definite. So this is why we say it's jointly concave in V. So it's quite straightforward to conduct MLE for the MNL model if data is complete. For incomplete data, we will show some examples later. The III property, the independence of irrelevant alternatives, basically, as we said before, the ratio of the choice probabilities for any two items is independent of others. So that's the II property. Some people may say, okay, this one is too special. The substitution pattern is too restrictive on the MNL model. So that's why here we can extend the MNL model to nested logical model. Basically, here we say the products, the alternatives can be grouped into M nest. And the utility for any alternative J in nest I can be divided into three terms. The first term Uij, we can still call it a nominal utility as deterministic. And we have two random terms. Psi I indicate the randomness at the nest level. This one is the same for all products, for all alternatives in nest I. This one, the random term Psi Ij, is IID gamble random variables with a scale parameter mu2i for all items in nest I. Now we have another assumption. We assume the sum of the two random terms follows another gamble distribution with a scale parameter mu1. Mu1 is greater than mu2i. And then under the random utility maximization framework, we can have the choice probability in closed form. Here is the choice probability for any alternative J in nest I. You can see here the choice probability has two terms. The first part indicates the choice probability for nest I. You can see this one looks like the MNL. The second part represents the choice probability for alternative J in nest I. This one is another MNL. So that's why we call this model nested logic choice model. Now, here we have a proof for nested logical model. The framework is still the random utility maximization framework, or the RUM. The gamma random variable have very good properties. For example, the maximum of multiple gamma random variable is still gamma random variable with the same scale parameter at different means. And here, so that's why we can consider the maximum of the random utilities for all the products in the same nest as a new random variable. We first find the choice probability for the nest, and then we work on the choice probability within the nest. Basically, here is the structure for the nested logical choice model. All right, here is the mathematical formula, and we can get the choice probability for the nest. All right. Actually, the proof is very similar to the one for the MNL choice model. Here, this part is quite important. And first, we get the choice probability within a nest I. This is the choice probability for any item j in nest I, and then we can get the choice probability. This part for nest I, basically is this part, right? You can see this is how we get the choice probability in closed form on the nested logical choice model. Again, the principle is a random utility maximization framework. And the choice probability for each product, for each item, is equal to the probability its utility is greater than the utility of any other item in the opposites, right? So and here we need some assumption. For example, the gamma distribution, the IID gamma distribution. And here on the nested logical choice model, we have randomness at the nest level. It is the same for all products in the same nest. And then we have another randomness at the product level. We can further generalize the MNL and nested logical choice model. Here is the generalized extreme value of the GV model. Actually, the MNL and the nested logical choice models are special cases of the GV. In the GV model, the very important part is generating function. The generating function has some properties. For example, here is a homogeneous of degree 1, and it approaches infinity as any UI goes to infinity. And the partial derivatives with respect to k distinct variables exist, and is non-negative if k is odd, and non-positive if k is even. And then we can have the choice probability for any item I in S. And we can show that the MNL and the nested logical choice model are special cases of the GV. The key part is to find the appropriate generating function beside U, right? Here we want to go further a little bit. This one is slightly different from the M&L. Here we call it M&L with a non-randomness. In the standard M&L choice model, we know the product utility has two parts: the nominal utility that is deterministic, and the random utility that is IID gamma random variable. Here we say there is a little bit different. One of the alternatives could be the outside option or no purchase option, whose utility is deterministic. Here, generally speaking, let's say the utility for an item I prime is deterministic. Okay, see this one, the utility does not have the random term cosine I prime. The framework is still random utility maximization framework. So the choice probability for any item I is equal to the probability UI is greater than uj for any j, and ui is also greater than the deterministic utility ui prime. That is the choice probability for any item I. Actually, there are closed form expressions for the choice probabilities. You can see for any item I whose utility has two parts, the deterministic utility and also the random utility, we find the choice probability is a little bit more complicated than M&L because it has two parts. The first part looks like M&L model. The second part is adjustment. For the special item, I prime, whose utility is deterministic, does not have the random term cosine I prime, the choice probability qi prime is equal to exponential of a negative number. You can see the choice probabilities are well defined. The non-negative, the sum is equal to 1. This one is different from the standard M&L choice model. Actually, we can show this one. It's not even a GV model. GV model is a large class of discrete choice models. The M&L next logic choice model or many other logic choice models are special cases of the GV model. But this one, the M&L with a non-randomness is not a GV model. All right, and now let's consider some operations programs. The first one is the price optimization and on the choice models. Pricing is an effective marketing and retailing strategy. And in monopoly, we can consider multi-product price optimization to maximize the aggregate expected revenue or profit. We focus on the structure of the optimal pricing strategy. And in the oligopoly, there are multiple firms, and it's a multi-product price competition. We want to find the price equilibrium. We want to develop efficient algorithms to compute the equilibrium. We want to find the properties of the equilibrium. We want to identify the impact of the price competition. There are lots of very interesting work for price optimization and price competition on many different discrete choice models. Here, just very, very briefly, I want to present a showcase about the price optimization on the standard M&L choice model, because this is the nature of the tutorial presentation. The market size is normalized to 1, and CI is the unit cost for product I. We assume the fixed cost for each product can be ignored in price optimization because the products are already there. The firm chooses prices for all products in its offset S to maximize the total expected profit. And we can have the mathematical formulation. This one, PI minus CI is the profit margin, and this one is the choice probability under the M&L choice model. One represent the attractiveness of the new purchase and outside option. We find for this one, the multi-product price optimization. We find some interesting structure for the optimal prices. The first one, adjusted markup. Adjusted markup, the definition is the markup P minus C, the profit margin, adjusted by 1 over beta. Beta is the price coefficient under the M&L choice model. We find this one, the adjusted markup is product invariant at optimality. That means this term is the same for all products in the offset. We can denote this one as theta. And then we can find the total profit function as unimodal in theta. You can see this one is one-dimensional, is continuous, and is unimodal in theta. So it's very easy to find the optimal adjusted markup of theta. And immediately we can find the optimal prices for any product in the offset, right? Here we introduce an alternative approach because under the M&L model, there is a one-to-one mapping between the price vector and the choice probability vector. You can see here we can express the price PI in terms of choice probabilities Q. The optimization in prices becomes optimization in choice probabilities. Here you have a new formulation. The decision variable is the choice probabilities. We find that this one, the aggregate profit function is jointly concave in the choice probabilities Q. So we can use a convex or concave optimization to find the optimal choice probabilities. And then we can use the one-to-one mapping between the price vector and the choice probability vector to find the optimal prices. All right, we can extend our result to multi-stage nested logical choice model. Here we consider price optimization under the nested logical choice model, the two-stage nested logical choice model. And again, under the same assumption. P minus C is the profit margin, and then we have the choice probability under the nested logical choice model. The choice probability true part, the choice probability for the nest, and the choice probability for each product within a nest. All right, we have a similar result. First one, adjusted markup is the same for all the products in the same nest. And again, we can define adjusted nest level markup. We can have nest level markup for each nest. We find this one is also the same for all nests. And then the original multi-dimensional optimization problem can be simplified to a single dimensional problem, right? And moreover, we can find under the GV model, the markup is also the same for all the product at optimality. And then we move to assortment optimization. In assortment optimization, because here we consider some scenarios, the firm is not allowed to change retail prices. If you want to sell this product, you got to charge the manufacturer suggested retail price. Or there may be price formula decided at the high level for all products. For example, 10% markup across the board. Or if you frequently change your prices, and it may induce some strategic purchase behavior. Some consumers may delay their purchases. They won't wait for cheaper prices in the near future. But still, the firm can do some operations decisions. Here, the firm can decide which products should be carried in its store or presented to arriving consumers. And then we can have the formulation for assortment optimization as the typical combinatorial program. And the firm chooses an offset S to maximize its aggregate expected revenue. And here the decision variable is the product offset. So, and for each product, the decision is to make a choice, offer it or not to offer it. So it's a binary. So that's why we call it, and we see this one is the typical combinatorial program, right? How to solve the assortment optimization problem. For some special cases, we can find the optimal solution very easily. For others, it may be hard to do so. First, we introduce the concept revenue order assortment. Basically, here we change the product labels and such that the products are labeled in markup or decreasing order. Or if you want to maximize total revenue, you can label product in price decreasing order, right? And the revenue order assortment SI, that means you offer a product 1, 2, 3, 4 up to I. This is the revenue order assortment. You can see they are up to big M. This many revenue order assortments. And we consider some conditions for discrete choice model. The first one, the choice probability, Qi, can be expressed as the function of the choice probability Q0 for the no purchase outside option. If there is a relationship between Qi and Q0, and if the relation is convex. And then we can say a revenue order assortment is optimal for the assortment optimization on a general discrete choice model. How to prove this one? Here, just very briefly to talk about the schedule proof for the revenue order assortment, or is the optimality for the assortment optimization program. We let QS be the total choice probability for all products in offset S. And we can always find a K such that the choice probability for all products in the optimal offset S star is the optimal offset. And we can find two revenue order assortment, SK minus 1 and SK, such as these inequalities are satisfied. And then we find parameter gamma. Gamma is between 0 and 1, the convex combination of the total choice probabilities of SK minus 1 and SK is equal to total choice probability for all products in the optimal offset S star. And immediately we can find this one. All right. By convexity, we can show and the combination of the choice probability for any item j in the random order assortment sk minus 1 and sk is greater than the choice probability in the for product j in the optimal offset S star. And finally, we can show the convex combination of the total revenue or the total profits of the revenue order assortment sk minus 1 and sk is greater than the total profit or revenue of the optimal assortment S star. And then we can say one of the assortments sk minus 1 and sk must be optimal. This is how we show the optimality of the revenue order assortment for the assortment optimization problem on the discrete choice models. But we need some conditions. But generally speaking, the assortment problem could be NP-hard. And if the problem is NP-hard, we may want to find some heuristics with good performance guarantee. Or we can develop some approximation scheme. We can find a near optimal solution. Here is an example. Here is the assortment optimization problem on the MNL with a non-randomness for the outside option, like we said before. The utility of the outside or no purchase option is not random, it's deterministic. And the resulting choice model is no longer MNL. I call it MNL with a non-randomness. It's not even a GEV model. Here is the choice probability. All right. And then we can show this one, the assortment problem is NP-hard. For this NP-hard problem, we can study some heuristic, like the revenue order assortment. We know there are not many revenue order assortments, only up to n. We can show the optimality. Actually, it's not optimal. It's near optimal. It depends on the parameters. For example, here, if the choice probability for the no purchase option at optimality is greater than tau, we find the revenue order assortment is this much optimal. For example, if Q0 star is greater than 50% and the revenue order assortment is 69% optimal. Actually, in practice, many consumers choose a no purchase option. That means it's likely the choice probability for no purchase option at optimality is much greater than 50%. And then we can find the optimality level is much better for the revenue order assortment. We can further develop some approximation scheme, like the fully polynomial time approximation scheme. Here the idea is to use dynamic programming to find offset such that the value is very close to the value at optimality. We can find the objective function here has the three part, the numerator and the denominator, and here is the inside of exponential. Where the idea is to discretize all the parameters and solve DP, so many DPs, and return the best solution. Actually, we can show this one is near optimal. Actually, it's the FP+. The idea at the high level is to solve, is to discretize the parameters and solve dynamic programs. All right. Next, I want to briefly talk about some issues in the estimation. Actually, when we work on practice, there may be some issues in the data because here, we want to estimate the models. We want to calibrate the parameters in the chosen models. The data may not be the one we want. So there may be some missing data issues. Here, I want to briefly present an example to show you how to deal with some missing data issues. We consider the MNL with a non-randomness, a little bit more than the standard MNL choice model. And here is the data. There are k observations. In each scenario k, the set of all available alternatives is denoted by this one, and the usage of some alternative may be deterministic. We don't know which one, and it could be the no purchase or the outside option denoted by 0, right? We know the product information, like we said before. This one is the attribute values. Price could be one of the product attributes. And on the linear attribute utility assumption, we can write on the nominal or the intrinsic utility. The data is the typical sales data. It could be aggregate level or the individual level. Okay, suppose the aggregate data is complete information. And NKI consumers purchase product I in scenario K, NK0 consumers choose the outside option, and we have some notation. We also assume the market size, the random variable. You realize the market size is also included in the complete data. Basically, it's equal to the number of consumers in each scenario. We take the maximum likelihood estimation of the MLE approach. The likelihood function in complete data case can be written in this way, as is a likelihood function. We have two sets of parameters to estimate. The first one is the market size parameter. Actually, here is the parameter for the Poisson random variable. Second one is V is the vector that the V indicates the attribute coefficients for consumer choice behavior. Immediately we can have the log likelihood function. Actually, the log likelihood function has two parts. The first part is the log likelihood function for market size. The second part is the log likelihood function for consumer choice. And all right, so again, the choice probability in this case is the MNO with a non-randomness. All right, in the complete data case, we maximize the log likelihood function because the log likelihood function has two parts. For the first part, regarding the market size, we find the maximizer is lambda hat. It's just the sample average for the market size. Next, we focus on the estimation problem for V, the attribute coefficients. We find this one, the choice probabilities are quite different from the MNL. And luckily, we find the log likelihood function is still jointly concave in the attribute coefficient V. Here we can show you the Hessian matrix has 3 parts. The first part, second part, and third part. All 3 parts are negative semi-definite. So that's why we say, the log-likelihood function is jointly concave. So we can very easily to maximize the log-likelihood function to find the attribute coefficients V for the MNL with the non-randomness in the complete data case. Right? So if the data is incomplete, when we talk about practice, the outcomes for the outside option are not available. Is the case in the sales data. All the sales of competitors are not included in the focal from the sales data. You don't have access to the sales data of your competitors. You only know your sales data. If you consider the marginal likelihood, here is the marginal likelihood. You can see it's much more complicated than the regular likelihood. So it's usually harder to directly solve the MLE problem for the incomplete data. So that's why we consider some alternative approach. For this case, we consider expectation maximization, the EM method. All right. Again, we take the log likelihood function. The log likelihood function, you can see we try to connect the log likelihood function on the incomplete data to the one on the complete data, because we already derive a very good structure, very good properties for the complete data case. Right? We want to connect these 2 problems. The EM algorithms, the EM algorithm has 2 steps in each iteration. It's the iterative algorithm. In the E step, we update the expectation of the number of consumers who choose the outside option. If you don't know the actual outcome for that option, we can update the expectation in each step, actually in each step. And then in M step, we solve the maximization problems for market size and for the attribute coefficients V. We find that this one is quite straightforward, because for the market size, we have closed form expression. And for the consumer choice behavior, we find, this one, the log likelihood function is the jointly concave. So this part is quite easy to proceed. Here we have full distribution for the EM algorithms. Basically, for the EM algorithm, it's the iterative algorithm. And each step, in each iteration, we have 2 steps. The each step, we update the unknown outcomes. In the M step, we maximize the log likelihood function to find the market size parameter and also the choice probability parameters lambda and V. The EM algorithms has very good property. The log likelihood function monotonically increases each step, so it converges to the value at a stationary point. Actually, in practice, we find that this algorithm converges very, very fast. All right, for the nature of the tutorial presentation, let me briefly talk about other issues in the discrete choice model. The model we just described, they are parametric choice model. There are parameters in the choice probabilities. Actually, there is another set of choice model, the non-parametric choice model. And there is the preference list for all the alternatives. including the no purchase outside auction. So consumers choose the available product that ranks the highest. There may be some issues like we said before, the estimation issues, how to estimate the choice probability. And there may be some operations programs, like for example here, assortment optimization. Another issue is the pricing. When we consider pricing, because here when you change your product prices, the preference list may change as well. So we got to figure out how the preference list changes as the price with respect to product prices, and then we can work on price optimization program. Another issue is about the social cost, because here we consider rational consumers. There may be some uncertainty regarding product utilities. In practice, consumers collect product information without utility uncertainty. And after they figure out the product utilities, and they choose the one they like the best. They choose the one that give them the largest utility, the net utility. Here we say, collecting product information is costly, is time consuming. There may be a search cost. How can we incorporate such cost into consumer search and choice behavior? That's a big issue here. So that's the modeling part. After the modeling part, we may consider some operations programs like assortment planning, pricing, or the estimation. Right. Another issue, sequential choice. Sequential choice is different from simultaneous choice. In the simultaneous choice, we know, consumer observe product utilities simultaneously and choose the one with the largest utility. But in practice, in some scenarios, things may be different. Consumers may search a product one at a time, sequentially. So optimal stopping is a very important issue here. When are you going to stop searching and make a purchase? After figure out the consumer search and choice behavior for the firm, what can the firm do? The firm may consider sequential offerings, offer different sets of products, depends on the decision, depends on what they observe. And we may also consider heterogeneity of consumers. Consumers can be different in many different ways. So here for this one, they may have different paying level. So after you offer, after the consumer see one set of product, two sets of products, they may decide to leave, to visit another store. There is lots of literature on sequential choice. Right? Consideration set is a very interesting topic in consumer choice behavior, because in practice, most consumers don't consider all products because there are so many. It's time consuming to consider so many products. It may be practically impossible to do so. So in practice, some consumers may first form a consideration set. It's a subset of all the available products. They may consider product features, they may consider prices, they may consider the search cost. So it's a two-stage consider, then choose a model. Threshold can play an important role here. Like the consumer can use a threshold to form a consideration set. The threshold may be something about the nominal utility. The product cannot be too bad. Otherwise, I won't consider it, I won't buy it. Or some consumers may have budget constraint. They only consider products in this price range. And you can see they have different ways to form a consideration set. and the choice behavior can be quite different for different consumers. There is lots of literature on consideration set choice model. Another issue is about multiple purchases. In all the model we just discussed, we assume consumers choose one item, at most one item. But in practice, in some scenarios, some customers may purchase multiple products or multiple units of the same product. And we may want to figure out why consumers purchase more than one. Here is about the relationship among products, substitution, complementarity, or both, or budget. There is also, although it's a new topic, there are also some existing works on the multi-purchases. All right, let me briefly summarize this tutorial presentation. We briefly review discrete choice models. We talk a lot about the utility based on choice models, and we consider sequential and simultaneous choice, and search cost can be part of the behavior, search and choice behavior. Consideration set plays a very important role in the search and choice model. And we also showcase how to develop new discrete choice model, as is very important, especially when you want to incorporate new features into existing choice models to study the impact of the new feature on consumer choice behavior and what's the impact on the firm's operations decisions, and how to calibrate the new feature by using real data in different data structure. We consider operations problems, the multi-product price optimization and the competition. And we also consider assortment optimization problem. It's a typical combinatorial problem. We try to characterize the structure for the optimal solution, or develop some heuristic with good performance guarantee for some NP hardware problem. We want to develop an approximation like the FB does. Finally, we want to use the data to estimate the choice models, to calibrate the parameters in the discrete choice models. And we want to develop some efficient estimation algorithms. And meanwhile, we may also want to resolve some issues regarding the data, for example, missing data. Again, my final words, discrete choice model is a very, very important topic. And I hope you find this tutorial presentation interesting and useful. Thank you very much.